Welcome to Educator.com. In today's lesson, we're going to be solving compound and absolute value inequalities. A compound inequality consists of two or more inequalities combined by either and or or. To solve a compound inequality, solve each part. For example, if you are given 4x minus 2 is less than 10, and x minus 1 is greater than or equal to 4, it's connected by the word and, so it's a compound inequality. So I'm going to solve each part of that. So 4x, add 2 to both sides, that would be less than 12. Divide both sides by 4, so x is less than 3. And if I add 1 to both sides, I'm going to get x is greater than or equal to 4. We'll talk in a second about how the solution set works for this, but the first step is to just solve both parts of the inequality. Same idea if an inequality is a compound inequality connected by the word or. For example, you might be given 3x is greater than 6 or 4x is less than 4. Again, solve each part. X is greater than 2 or x is less than 1. So breaking this down and talking about the solution sets for each. If and is used, the solution set is the intersection of the solution sets of the individual inequalities. So I'm going to review this here, the idea of intersection, and this is also covered in detail in the Algebra 1 series. So intersection means the common members of both solution sets. Just looking at numbers, if I have 2, 4, 6, 8, and 10, and that's my first set. And then I have a second set that is 6, 8, 10, 12, and 14. The intersection would be the elements common to both. So I see that I have 6 in both, 8, and 10. So the intersection would be 6, 8, and 10. Applying that to inequalities connected by the word and. For example, x minus 4 is less than 10 and 2x is greater than or equal to 4. Okay, solve each part as discussed. So add 4 to both sides. This means that x is less than 14 and, so both conditions must hold. If I divide both sides by 2, I get x is greater than or equal to 2. To visualize this, look at the number line. So if I have 0 right here, and then 2, 4, 6, 8, 10, 12, 14. This is telling me that x is less than 14. And that would just go on and on and on. This is telling me x is greater than or equal to 2, which is going to start here and go on and on and on and on. But I'm looking for the intersection or the common elements. And the common elements would be greater than or equal to 2 and less than 14. So the intersection would come out as 0, 2, 4, 6, 8, 10, 12, 14. Greater than or equal to 2 and less than 14. And you could write that, write that out as an inequality or as using set notation that x is greater than or equal to 2 and less than 14. So this is actually just a more efficient way of writing instead of two separate sections here with the word and. You can just write it out more efficiently like this. X is greater than or equal to 2 and less than 14, or showing it on the number line like this. So that is for inequalities joined by the word and. If or is used in a compound inequality, the solution set is the union of the solution sets of the individual inequalities. Now, reviewing what a union is, just using numbers. If you have a set such as 4, 5, 6, 7, 8, and then you have another set -2, -1, 2, 3, 4, 5. And you're asked to find the solution set. You're asked to find the union. Well, the union is any elements that are in either one of these or both. So if it's in one, if it's in the other, or if it's in both, that would be the union. Now, I'm looking and I have 4, and that's actually in both. I don't need to write it twice. 5, okay. 6 is just in this one, but it's included. 7, just in that one. 8, and then I already covered 4 and 5, but I also have to include -2, -1, 2, and 3. So, and I could rewrite this in ascending order, but it's all included here. So the union means that it includes the elements that are in either one of these or both. Applying these to inequalities, applying this concept to inequalities, 3x plus 2 is greater than 8, or 4x minus 3 is less than 1. So compound inequality joined by the word or. First, solve each inequality. So 3x is greater than, subtract 2 from both sides. So 3x is greater than 6. Divide both sides by 3 to get x is greater than 2. Or, solve this one also. If I add 3 to both sides, I'm going to get 3x is less than 4. I'm going to divide both sides by 4x to get x is less than 1. Now, looking at this on the number line, what this is saying is 0, 1, 2, 3, 4. This is saying x is greater than 2. This is saying x is less than 1. And there's no overlap here, but that's okay because the union means that if something's in either one of these or both, it's included. So this is saying that the solution set is that x is greater than 2 or x is less than 1. And this can be written in set notation. So I would write it as x is greater than 2 or x is less than 1. So when you use and, it's the intersection of the two solution sets. When or joins a compound inequality, the solution set is the union of the two solution sets. Now, we've worked with absolute value equations, and this time, today, we're working with absolute value inequalities. To solve an absolute value inequality, you need to use the definition of absolute value. And recall that the definition of absolute value is the distance that a value is from 0 on the number line. So the absolute value of x equals, the absolute value of 3 is 3 because the distance between this and 0 on the number line is 3. The absolute value of -3 is also 3 because the distance between -3 and 0 on the number line is 3. So the absolute value of 3 is 3 because it's 1, 2, 3 away from 0 on the number line. The absolute value of -3 is 3 because -3 is also 3 units from 0 on the number line. For more complicated problems, you may need to rewrite the inequality as a compound inequality. So talking about this in a little bit more detail, you may see two different forms. You may see inequalities in the form the absolute value of x is less than n. If you see that, rewrite the inequality as a compound inequality as follows. Looking at this with an example, the absolute value of x is less than 4. Think about what this is saying. It's saying that the absolute value of x is less than 4 units from 0. Okay, so anything that is less than 4, so it could be 3, 2, 1, but it's less than 4 away from 0. That could be satisfied by anything between 0 and 4, but it can also be satisfied by anything between 0 and -4. Because the distance between -4 and 0 on the number line is less than 4. -3, the distance between that and 0 is less than 4. So anything in this range is going to satisfy it. So what this is really saying is that x is less than 4 and x is greater than negative 4. For example, if x, so in order for the answers to fall in this range, they can't just be less than 4 and go all the way down, because then you get numbers way over here that have an absolute value that's much bigger than 4. So it's in this range where x is greater than negative 4, but less than 4. So in general, when you see an absolute value in this form, where it's less than something, you rewrite it as two related inequalities. X is less than 4, and x is greater than negative 4. Or just generalizing out, the absolute value of x is less than n can be rewritten as x is less than n, and x is greater than negative n. Okay. The other possibility is that you have inequalities are in the form the absolute value of x is greater than n. For example, the absolute value of x is greater than 3. Well, what that's saying is the absolute value of the number is more than 3 away from 0 on the number line. So it's anything bigger than that, anything bigger than 3 is going to have an absolute value of greater than 3. 4 has an absolute value greater than 3, and on down, on up. In addition, however, if I look over here on the left, any number smaller than negative 3 is also going to have an absolute value that is greater than 3. If I took negative 4, the absolute value of that is 4, which is greater than 3. So this would translate to x is greater than 3 or x is less than negative 3. So you need to memorize these two forms and be familiar with them. And generalizing this out, this would say that the absolute value of x is greater than n could be rewritten as x is greater than n or x is less than negative n. So you need to keep these in mind. When you see x, the absolute value of x is less than n, you rewrite it as x is less than n and x is greater than negative n. When you see the absolute value of x is greater than n, then x is greater than n or x is less than negative n. And you can apply these to more complex inequalities such as 4x plus 1 is greater than or equal to 12. I would recognize that it's in this form, and I would rewrite it as the 4x plus 1 is greater than or equal to 12, or 4x plus 1 is less than or equal to negative 12. So just following this pattern. And we'll work on this in the examples. Okay, starting with example 1. This is a shorthand way of a compound inequality that is joined by the word and. So instead of writing out 7 is less than 14x minus 42 and 14x minus 42 is less than or equal to 35, they just combined the same term, put it in the middle, and left these on the outside. But this is really a compound inequality that is joined by the word and. And remember that in order to solve these, you solve each inequality, and then you find the intersection of their solution sets. So for absolute equalities joined by the word and, we're going to need to find the intersection of the solution sets. All right, let's solve each of these. That's the first step. So I'm going to rewrite this with the x on the left. So 14x minus 42 is greater than or equal to 7. More standard. So it's the same, it's saying the same thing. 14x minus 42 is greater than or equal to 7. I just reverse the sides of the inequality. Next, add 42 to both sides. And that's going to give me 49. 14x is greater than or equal to 49. Now divide both sides by 14. And since that is a positive number, I don't need to reverse the inequality symbol. I can simplify this because they have a common factor of 7. So that would, to simplify this, remove the common factor. That's going to give me 7 halves. So I just pulled out the 7 from both the numerator and the denominator, factored it out. Okay, Solving this inequality, my second inequality. Adding 42 to both sides. It's going to give me 14x is less than or equal to 77. Again, dividing both sides by 14 is going to give me 77 divided by 14. Again, I have a common factor of 7, so this is going to give me 11 halves. Now, the intersection of these, graphing this out, well, this is 2, 4, 6. So this is about 3.5, 3.5. So, and this is equal to 5.5. Okay. To help me graph it out, I'm going to write it in decimal form. 1, 2, 3, 4, 5. A little more room. 6. Okay. So what it's saying is x is greater than or equal to 3.5, which is right here. And it includes that point 3.5. So I'm going to put a closed circle. Here, the other restriction is that x is less than or equal to 5.5. So this is greater than. It's going up this way. But I have to stop when I get to here because the intersection of the solution set has to meet both conditions. It has to be greater than or equal to 3.5 and less than or equal to 5.5. So I can write it like this as an inequality. I can graph it here or set notation where x is greater than or equal to 7 halves and less than or equal to 11 halves. Okay, again, recognizing this is really a compound inequality, and it's joined by the word and, but it's just a shorthand way of writing it. So I wrote this out as two related inequalities, solved each, and found the intersection of their solution sets. The second example is a compound inequality joined by the word or. So I'm going to go ahead and solve both of these and find the union of the solution sets. Adding 7 to both sides, it gives me 3y is less than or equal to 15. Divide both sides by 3, y is less than or equal to 5. On this side, subtracting 10 from both sides to get 2y is greater than 16. Dividing both sides by 2 gives me y is greater than 8. Okay, since this is or, it's the union of the solution sets, so any element of either set or that's in both sets would be included in the solution set for this compound inequality. So here I have y is less than or equal to 5. And here I have y is greater than 8. So all of this is included and all of this is part of the solution set. Could also be written as y is less than or equal to 5 or y is greater than 8. Okay. The third example involves an absolute value inequality. When I look at this, I just want to think about which form this is in. And this is in the general form. The absolute value of x is less than n. And recall for those that you could rewrite this and get rid of the absolute value bars by saying x is less than n and x is greater than negative n. So that's the general form. So I'm going to rewrite this as 2z minus 6 is less than or equal to 8. So that's this form. And 2z minus 6 is greater than or equal to negative 8, which is this form. So it's really important to memorize these or understand them well enough that you can apply them to more complex situations. Now I'm going to solve each. 2z minus 6 is less than or equal to 8, adding 6 to both sides to get 14. Dividing both sides by 2 to get z is less than or equal to 7. And I need to solve this other one. I'm going to add 6 to both sides to get 2z is greater than or equal to -6. Z is greater than or equal to -3. And since I'm dividing by a positive number, I don't have to worry about reversing the inequality symbol. Okay. So I end up with a compound. Again, I had an absolute value inequality in this form. So I solved both inequalities. Actually, I made a little mistake here. Let me go ahead and correct that. 2z minus 6 is greater than or equal to -8. So 2z is greater than or equal to, this is actually going to be -2. So adding 6 to both sides is going to give me -2. Now, if I divide both sides by 2, that's going to give me z is greater than or equal to -1. Okay. You can either leave this as it is, or you can go ahead and graph it out. And since this is end, the solution set needs to meet both of these conditions. So -1, 0, 1, 2, 3, 4, 5, 6, 7. A little more. Let's go to 8. Okay, so z is less than or equal to 7. So this is going to go on and continue on. But it also has to meet the condition that z is greater than or equal to -1. So anything in this range is going to be the intersection of the solution set for these inequalities. Also writing it out using set notation, what we have is that z is greater than or equal to -1 and less than or equal to 7. So 3 different ways of writing out the solution set. Okay, next example, also an absolute value inequality. And this one is in the form, the absolute value of x is greater than n, in this general form, which can be rewritten as x is greater than n or x is less than -n. So rewriting this and removing the absolute value bars as 2 different inequalities, 3w minus 8 divided by 5 is greater than 4, so that's this first form, or 3w minus 8 divided by 5 is less than -4. Okay. First thing to do is get rid of the fraction. So multiply both sides of this inequality by 5. Next, add 8 to both sides. And finally, divide both sides by 3. For this inequality, again, get rid of the fraction, multiply both sides by 5. Add 8 to both sides. And divide by 3. This is joined by the word or, and 28 over 3 is, I'm going to rewrite that as 9 1/3. So w is greater than 9 1/3, or w is less than -4. To graph this, -5, -4, -3, -2, -1, 0, 1, all the way to 9 1/3. Okay, so this is saying that w is greater than 9.3, or it's less than -4. Open circle, because it's a strict inequality. Set notation would be w is greater than 28/3, or w is less than -4. So recognizing that this is in the general form, the absolute value of x is greater than n, I rewrote this as 3w minus 8 divided by 5 is greater than 4, or the same expression is less than -4. Solving each one and the solution set is the intersection of the solution sets of those two inequalities. That concludes this lesson of Educator.com, and I'll see you soon.